Okay, want to develop, basic rules for derivatives. After a while, you see like patterns. Okay, so it's a little too insane to always invoke the limit definition of the derivative to find the derivative. So obviously, here I am worried about, jeez, stupid pen is out of ink. Looks like we're gonna have to go for green. Yeah, so anyways, if we have something like f of x equals x squared, it just becomes insane after a while to always go back to this limit definition of the derivative. Especially because, people have studied these things long enough that they see little patterns. And you could approach it via these basic rules. Let's see what we got here. Well, one of the most basic rules is the power rule. Okay, and that's kind of what I'm after right here. So basically, how do I take the derivative of polynomials? Turns out to be pretty simple. Okay, so anyways, we're using x plus change in x in the here. Okay. I got it. Let's change in x goes to 0. We got to FOIL this character out, so we get x squared plus 2x change in x plus change in x squared minus x squared all over change in x equals the limit as change in x goes to 0 of, okay, these x squares cancel. We got 2x change in x plus change in x squared all over change in x. Okay. Right now its form is indeterminate. If you plug in change in x equals 0 here, you'll get 0 over 0. Okay, that's bad news, right? So you have to use some of our tools to figure this one out. So I think if we factor out a common factor of change in x, we'll be able to simplify it. Such that the result will be equal to this thing, except that change in x equals 0. And then we have a theorem which says that's okay. We just care about approaches. We don't care about the actual value there. Okay, taking the limit, change in x goes to 0. So the only thing you're plugging in for is the change in x. Right? We're plugging 0 in for change in x, and then we'll be left with 2x. So we kind of look back at this guy and ask ourselves, how does this guy relate to this guy? Turns out that it looks like all I'm doing is taking this exponent and kind of flopping it in front, and then subtracting the old exponent by 1. Okay, so this exponent is currently 1. If you did some more experimentation, which is probably, somebody had to do somewhere, for example, looking at x cubed and then getting its derivative via the limit definition. The derivative there would be 3x squared. If f of x equaled 4, let's say, sorry, x to the 4th, then its derivative is 4x cubed. If f of x equaled x to the 5th, and you went through this limit definition thing, you would get f prime of x equals 5x to the 4th. Okay? So you kind of see a pattern. And I mean, you have to prove patterns in math, using induction or whatever means are available. I think the book uses maybe the binomial theorem or something when they prove this idea. But for us beginning calc students, I think it's good enough just to note that when you have some sort of exponential term like this, it's not exponential, but like a polynomial term, a monomial, all you have to do is bring down the exponent and put it in front, and then subtract the old exponent by 1. So it's a general rule, and that's what we're after in these next couple sections. It's just general rules for taking care of these derivatives without having to go to the limit definition. So this rule we're talking about is the most fundamental rule. Okay. 5 seconds after you're dead, you should be able to remember this rule. And basically, the derivative of x to the n is equal to nx to the n minus 1. Okay? Just bring down the old exponent and subtract the n by 1. That's what you get. Alrighty then. Let's make this more official now and go into my notes for this section. 3.2, basic differential rules, and then they talk about rates of change. They're probably going to talk about velocity and stuff. Let's see, basic differential rules, differentiation rules, and some other stuff. The first one is the constant rule. Basically, the derivative of a constant is equal to 0. Okay. If nothing else, you could go through the proof of it, and it's not very illuminating, but you can view this thing as a function y equals c, right? So if we took y equals c and then graphed it, so it's a horizontal line going through the point C, its slope is 0. Okay? And that's what the derivative kind of tells us. It tells us slope at any point on this line. And so the slope is always 0. So the derivative of a constant is 0. Okay? And I always think of kind of derivatives as going downwards in my brain. And I think maybe that helps a little bit. I don't know. So if you have a constant going downwards to 0 somehow, I don't know. I guess you have to figure out your own ways to deal with this stuff, but that's how I think of it. The rule we just saw is the power rule. And again, what does it look like if you have the derivative with respect to x of a term like that? You just bring down the exponent n, and then you have x to the n minus 1. If you're really into math, some books will go into proving it's true for rational exponents and then other types of exponents, I guess. I'm going to steer away from that. I think it's, in the beginning, let's just learn how to ride the bike, and then later on we'll learn about other things. But yeah, so anyways, here's the power rule. Maybe one that for some reason the trivial ones are always the hardest, right? So how do I deal with x? It doesn't seem to have an exponent, right? It does. Just remember, if you don't see an exponent, there's a little 1 sitting there, right? So you think of it as bringing down the exponent 1 times x to the 1 minus 1. And then, for all x that's not equal to 0, that'll just equal 1. Because it would be 1. You think of it as 1 times x to the 0, which is just 1. Another way to think of it is the graphical kind of way. For instance, what is the graph of y equals x? Well, it's just the diagonal through the origin, right? So what's the slope of this thing? Well, the slope is 1 at every point. And there, again, there's kind of our answer just by intuitively looking at the slope of a line. Let's look at some of the problems in the book, I suppose. So here's number 6. So a simple one. Again, how do I do this? Well, you just hopefully you can think of it yourself. You bring down the 12 and put it in front, and then you subtract 12 by 1. Okay, so 12x to the 11th. Let's look at 4. Yeah, f of x is -9. The derivative of a constant is what? Well, it's 0. Right? So the derivative of y equals -9 will be 0. Let's see what else. Yeah, oh, here's a more interesting one. So you look at this and hey, you want to get in the habit of kind of like converting all radicals into exponents. That's the best way to go. After a while, it's kind of like, why do we even bother with roots and stuff like that? But so anyways, what I'll do is convert this into x to the 1/4, and that makes the mechanics a lot easier. So you bring down the old exponent, you bring down the 1/4, and then you subtract 1/4 by 1. So that would be 1/4 minus 4/4. Right? And of course, that's just -3/4. Typically, we'll try to avoid negative exponents. So you take that character and flop them down into the denominator, and that will be the end of the day. So it's 1/4x to the 3/4. If you want to get ambitious, you could rewrite it with your roots and all that stuff. So 1/4x. What is this going to be? The 4th root of x cubed, something like that. Okay. 4th root of x cubed. But usually this is good enough. Okay. The next rule is the constant multiple rule, so section 3. And we have all these rules. My intention is not that you sort of sit there and memorize these rules. The intention is that you get in there and you get your hands dirty and you practice with these, and the rules kind of become embedded in your brains. There's like the what do they call in educational science? I think it's chunking or something. You want to eventually have it kind of automatic, right? So in the beginning, I know you probably have to look back in your notes and stuff, but after a while, the hope is that you'll be handed a derivative and you'll just be able to kind of figure out or handed a function, then you'll be able to figure out the derivative. Anyways, the constant multiple rule is this: the derivative of the c times f of x is equal to, you could factor the c out of the derivative. Okay? This thing is a limit, and in the limit expression, you're going to have these constants floating in the difference quotient. Okay? And it just with any limit, you could factor out a constant. So here you can also factor out a constant and just sort of focus in on the function itself, taking the derivative of the function. Okay? So if you'd like, you could write c times f prime of x. Okay? So you kind of just ignore the constant in front and work. Okay, so for example, then, this is, I think it's example 5 in the book. Y equals 5x cubed. Okay. So what you're going to do is kind of just leave the 5 alone and take the derivative of this x cubed part. Okay. So for the x cubed, we learned how to do that in the last section. You bring down the 3, so 3, and then you have x to the 3 minus 1. So that'll be 5 times 3x squared, which is 15x squared. Okay. Part B, you got y equals 2 over x. Okay. Again, similar to what we did with the radicals, you want to rewrite this expression with an exponent. Okay. So instead of 2 over x, we're going to write 2x to the -1. And then we're going to take the derivative of x to the negative 1. So y prime, leave the 2 alone, and then maybe set up some parentheses for the x to the negative 1. Okay, so I'll bring down the negative 1. And then I have x to the negative 1 minus 1. And of course, that's just 2 times negative 1, x to the negative 2. And clean it up. You know, don't make somebody else do your laundry. Clean it up. So you have negative 1 times 2 is negative 2. X to the negative 2. And then, you know, you hate negative exponents. You put that in the downstairs. So it would be negative 2 all over x squared. What else do they have for us? It's part C now. F of t is 4t squared all over 5. Okay, you can reimagine this as 4/5 t squared. And then it's just, you know, this is a constant, and you're taking the derivative of this part. So it's f prime of t equals 4/5 times the derivative of t squared. So you just go 2t to the 2 minus 1. So you get 4/5 2t to the 1. And then we get 2 over 1 times 4 over 5. Of course, it's 8/5 t. So you get part D. You get y is 2 root x. And so again, we only, you know, you want to rewrite the square root of x as x to the 1/2. So you get 2x to the 1/2. And then take its derivative, so leave 2 alone. And then the derivative of x to the 1/2. So you bring down the 1/2. We got x to the 1/2 minus 1 this time. 2 times 1/2 is just 1. So I got x to the negative 1/2. And then that's 1 all over x to the 1/2. And x to the 1/2 is just square root of x. So I get square root, 1 over square root x. Okay. There's going to be derivatives such that when you take its derivative, you kind of see itself. And that's the way it is with these square root x's, right? So it's a little like y prime equals 1 all over y itself, but divided by 2. So you'd have to put a 2 up in the top. This is neither here nor there. It's just a weird observation. I mean, you're looking for patterns, hopefully, because you have all these rules to remember, and it can be overwhelming. Okay, especially during the summer, you only got fixed time. You got to figure out ways to kind of remember it. And the derivative of the square root is equal to some version of itself. Right? Later on, we'll see the derivative of the exponential is totally equal to itself. The derivative of e to the x is equal to e to the x. That's a very special guy. This guy is not as nice. But this guy is. I don't know. Let's keep on moving. Let's see part E. Getting back to reality here. Y is 1 all over 2 times the cube root of x squared. Okay, so again, you want to rewrite this so you could use our power rule. It's 1 all over 2 times x to the 2/3. And then we could rewrite that as 1/2 times x to the negative 2/3. Okay, so you get a little practice with those exponent rules. Okay, for the derivative, leave the constant alone. The 1/2, leave that alone. and maybe I'll leave some room for the derivative. So bring down the negative 2/3, x to the negative 2/3 minus 1. Negative 2/3 times 1/2 is negative 1/3. X to the negative 2/3 minus 3/3 is negative 5/3. So it's negative 1/3. I guess we could bring this downstairs. So negative 1/3 x to the 5/3. I'll probably just leave it like that. No sense in going back to the root symbols. Okay. So if you know, hopefully, okay. So note the derivative of something like a constant times this exponent thing, you can pull the 5 out, right? You can pull the 5 out and go d times over 5 times the derivative of x squared, so that'd be 5 times 2x to the first, and it's 10x. And that follows from the fact that the limit laws work that way. And the limit, if you remember, as x goes to maybe, let's say, 1 of 5x squared. You could rewrite this as 5 times the limit as x goes to 1 of x squared, and then do your substitute. So it'd be 5 times 1. Okay, so with limits, if you recall, we also had other laws. For example, limit as x goes to 1 of maybe x squared plus 2x. We could figure this out, obviously, by substitution, but if we had to invoke just the limit laws, it would probably look something like this. The limit of the sum is equal to the sum of the limits. Oops, geez, oh man. Right, so the limit of this plus this is equal to the limit of this plus the limit of this. So what am I getting at? Well, the derivatives have the same kind of deal going on. So if I want to find the derivative of x squared plus 2x, what you can do is just take the derivative of this and then plus the derivative of this. So take the derivative of the first one and then plus the derivative of the second one. Right? And this is just called the sum and difference rules. Let's go ahead and figure out this derivative. The derivative of x squared is just 2x to the 2 minus 1, so 2x to the 1. The derivative of 2x, well, I'll leave 2 alone. And then the derivative of x, if you remember, is just 1. Okay, so the derivative of x squared plus 2x is 2x plus 2. Okay, so you can basically, if you, at this point, you can take the derivative of any polynomial, hopefully. Right, so these are the sum and difference rules that allow us to do that. And again, the abstract business you see in the book, the derivative of f of x plus or minus g of x is going to be the derivative with respect to x, f of x plus or minus the derivative with respect to x of g of x. So, and if you have more than just 2 terms, that'll still apply. You can just take the derivative of the sum of the terms. So number 11, f of x equals x plus 11. So to find the derivative, just take the derivative of each part. Okay, so the derivative of x is 1, and the derivative of any constant is just 0. So 1 plus 0 is 1. And of course, this is just the equation of a line. And we can see its slope is 1. Okay, so there we get 1. Let's look at 16. And here we have a cubic. You take the derivative of the pieces. Y prime is the derivative of 4x. So leave 4 alone and take the derivative of x. The derivative of x is just 1. Minus 3 times the derivative of x cubed. So that would be 3x squared. And then clean it up. So you got 4 minus 9x squared. There it is. Okay. So any polynomial you should be able to do. Okay, derivatives of some of our transcendental guys then. We want the derivative of the sine and the cosine function, and then the derivative of the exponential e to the x, which I sort of already let the cat out of the bag there. So the derivative of sine and cosine, the derivative with respect to x of sine x is equal to cosine x. The derivative with respect to x of cosine x is equal to negative sine x. Okay. We might as well go through the limit, the sort of the limit proof of this fact. It uses some of the information that we've accumulated to this point. So note first the limit of sine of change in x all over change in x as x goes to 0 is 1. That was one of the definitions, or one of the limits we have memorized. We use the squeeze theorem to prove it. And then another limit we have, and this should be change in x, another limit we supposedly have memorized. Limit as change in x goes to 0 of 1 minus cosine of change in x over change in x. That one equals 0. And one other fact we need from trig, the sine of x plus change in x is equal to sine x cosine change in x plus cosine x sine of change in x. Okay, yeah, I mean, you don't have to worry too much. I'm not going to grade you over this. This is just hopefully convince you of the fact of these derivatives back here. But anyways, let's take a look. So given f of x equals sine x, I want to show that f prime of x is equal to cosine x. Okay, so f prime of x will be the limit as change in x goes to 0 of f of x plus change in x. So I'll have sine of x plus change in x minus sine of x all over change in x. Okay. Then I can use this statement to rewrite this guy here. So I'll have the limit as change in x goes to 0 of sine of x cosine change in x plus sine change in x cosine x and then minus sine x and then all over change in x. At this point, then I can break these guys. I believe we can break them apart and kind of use these factoids. So let's see how that'll work. Let's see where I want to split them. Okay, so I'm going to take, in a weird sort of way, I'm going to take these guys. Okay, so this will equal the limit as change in x goes to 0 of, so let's take this one first, this portion, sine of change in x cosine x all over change in x, and then the minus, I'm going to factor out a negative from these two parts. Okay, so it would be minus the limit as change in x goes to 0, because what I'm ultimately trying to do is kind of back engineer that form. Okay, so if I factor out a negative, I'd end up with sine x minus or sine x cosine change in x all over change in x. Okay, and then I can kind of see the parts that I need to work with. So I'll factor out a cosine x, and you could factor this out of the limit because cosine x is not dependent on change in x. It's like a constant. Okay? So I have cosine x times the limit as change in x goes to 0 of sine change in x all over change in x. And then minus, over here, you can factor out sine x. Okay, so it'd be minus sine x times the limit as change in x goes to 0 of 1 minus cosine change in x all over change in x. Okay, so this character then we know is equal to 0. I'm sorry, we know is equal to 1. Yeah, sorry about that. This character we know is equal to 0. So this will be cosine times 1 is just cosine x, and then this will be sine times 0, which will be 0. So we've shown through the limit definition of the derivative that the derivative of sine x is cosine x. Okay. Let's look at number, I don't know, let's look at least one of them, number 20. Or any example, I guess. So y equals 5 sine x. So we're also going to have to use the constant multiple rule. So you leave 5 alone and then take the derivative of sine, which is just cosine. So 5 cosine x. Let's try another one. Y equals negative 2 cosine x plus 3 sine x. So y prime will equal negative 2. We have the constant alone. The derivative of cosine is negative sine. And then plus 3 times the derivative of sine is cosine. Okay, and then clean it up. Negative times negative is positive 2 sine x. And then plus 3 cosine x. Okay, let's look at the derivative of the exponential. Okay, and this is the easiest derivative in the universe. And what does this mean? Well, it means that the slope at any point on the graph is equal to just the value of the function itself, which is kind of some craziness, right? It's weird. All exponential functions work like this. We'll see. Do we do this in this chapter? But eventually we'll see if you have the derivative of anything, like we'll say 3 to the x. It's just equal to itself times a constant, ln of 3. Okay. And you know, it's another one of these weird things where you have the derivative of y, some function, f of x or something, and when you take its derivative, you get the same thing back. You just get f of x times the ln of the base of f of x in this case. So in particular here, it'd be ln times some constant, f of x times some constant, excuse me. In the first case, the constant just turns out to be 1. Okay, so anyways, I don't know. There's that thing. I think it's a very important derivative. Let's see an example of taking its derivative. 51. F of x equals x to the negative 2 minus 2e to the x. So let's take the derivative f prime of x. Bring down the old exponent, so negative 2x to the negative 2 minus 1. Minus 2, so using the constant multiple rule, leave minus 2 alone. The derivative of e to the x is just e to the x. So it kind of looks like I didn't take a derivative, but I did. So here I got negative 2x to the negative 3. Let's just put that downstairs. So x to the positive 3 minus 2e to the x, and that's it. Okay, so an important application, obviously, of derivatives is finding instantaneous velocity, right? So here's part 7, rates of change. So if we're given s of t equaling some position function, we can get an average velocity by taking a difference of two positions and dividing it by time, right? So average velocity is kind of a, feet per second or something like that, miles per hour, like when you're driving your car. So here we have, how can I write this? Well, change in s, change in position, all over change in time is one way to write it. So maybe some backing for my paper, so it's a little easier to write. We can write this using our, it's basically the secant line formula again. So it's going to be a difference quotient, and if we take the limit of the difference quotient, it'll tell you the velocity at any, instantaneous value, or any particular value, like an exact speed at whatever time you want. So anyways, the difference quotient version here, s of t2 minus s of t1 all over t2 minus t1. Okay, so anyways, then we have this relationship between the position function and the velocity function, and the velocity function can be found by just taking the derivative of this. Of course, the velocity function will be the limit as change in t goes to 0, and this is instantaneous velocity now. Be the limit as change in t goes to 0 of s of t plus change in t minus s of t all over change in t, which is, of course, just equal to the derivative of the position function. So hopefully you can now appreciate the fact that, especially in physics, where you deal, I presume, with velocities and that kind of stuff a lot, acceleration, which will be the derivative of the velocity function, this is important. Derivatives are important, right? Anyways, in general, we can find eventually the position function just starting with a general acceleration by back engineering up the chain from acceleration. We can find this formula, s of t, which you've seen in your physics classes if you've taken physics. If not, there it is. Okay? So this is your initial position. This is an initial velocity. The g is acceleration due to the gravity. Let's look at one. So we have number 99. Some individual is dropping a silver dollar off of a building. I would recommend not doing that. Okay. So I have a silver dollar. We can model the scenario with that position function that I just showed you. S sub 0, the top of the building, is at 1,362 feet. And then if you're dropping a silver dollar off a building and you just hang it out there and then like, oh, the initial velocity must be 0 feet per second. So you're just holding it and then you let go. Okay. So we can fill out our position function, s of t, that must be equal to 1/2 times, what are we going, 32 feet per second squared? Is that how that works? Yeah, so 1/2 times 32 for our gravitational constant times t squared plus v sub 0 is 0 times t plus 1,362. Okay, let's clean that up. Let's get 16 t squared. That should be negative. Okay. Going downward. Negative 16 t squared plus 1,362. Okay, part A. They want you to find a formula for the velocity. Okay, so that's simple enough. Just take the derivative of the position function. So the velocity function is equal to the derivative of the position function, which will be equal to, leave the constant alone and take the derivative of t squared. So I have 2t. And then the derivative of 1362 is just 0. So my velocity function, negative 32t. Okay. Find the average velocity on the interval from 1 to 2. So even our cars have average velocity. Like, I have a menu in my car, and you can scroll through, and it'll tell you your overall average velocity. So anyways, find the average velocity. And it seems like your speedometer is more of an average velocity thing. I mean, it feels like it's an instantaneous velocity, but there's no way that, well, I don't know. I don't know at this point. But it seems like you know, it's a matter of measuring distances that the wheels spin or something. I don't know. But anyways, find the average velocity on the interval from 1 to 2 seconds. So the average velocity, we use not the derivative, but we use the difference quotient formula. So we're going to go s of 2 minus s of 1 all over 2 minus 1. Okay. So plugging 2 into my s of t formula and turning the crank, so I'll get 1298. And then likewise, plugging 1 into my formula, I get 1346. And that'll be all over 1. Okay. Putting that in my calculator, I get negative 48 feet per second. Part C, they want you to find the actual instantaneous velocities at time 1 and then times 2. Okay, so this time you use the velocity formula and just plug these in. So v of 1 obviously is just negative 32 feet per second. And then the velocity at time 2 is negative 64 feet per second. So let's just plug and chug at that point. Oh, what else they want to know? When does the silver dollar hit the ground? Okay, so that's just a matter of asking when is the position of the silver dollar 0. Okay, so plug 0 in for s. So 0 equals negative 16t squared plus 1362. And solve for t. So you factor out the 16. Remove the 16 over, 16t squared is 1362. We only want the positive solution, dividing by 16 first, obviously. But at the end of the day, we get about, what does that say, 9.23. T is 9.23 seconds. And then part E wants to know the speed of the silver dollar when it actually hits the ground, which you may be interested in if you're trying to figure out if it could hurt somebody. The velocity at that time. Okay, so you just put the t value into the velocity function. So v of 9.23 equals negative 32 times 9.23. And then that'll equal negative 295.24 feet per second. It's pretty fast. All right, that'll do it for this section. One way to help you along the way, make flashcards, okay? It seems elementary, but I mean, that's why we taught you that kind of stuff in grade school or wherever you learned it, in high school. These study skills are extremely important, okay? Especially when, you know, we only have like 1 month to learn all of differentiation. You know, compare that to the years you spent learning how to add and learning how to multiply and all that stuff. You know, we're not as generous with time now as we get closer and closer to the end of your degree. So, okay, that'll be it. Thanks for watching.